folks. Today we're going to be looking at a new topic. We're kind of changing gears. We're going to talk about some different ways we can represent an equation of a line in two dimensions. So today we're going to specifically talk about vector and parametric equations of a line, what they look like, and how we can come up with them. So to start with, I'd like to draw a vector that starts at the point 1 and 4 and has its head at the point 5 and 10. So its tail is at 1 and 4, its head is at 5 and 10. So there's my point for the tail. There's my point for the head. And I'll draw my vector starting at 1 and 4 and pointing at 5 and 10. And what I'd like to do with this vector is find the slope. So think back to grade 9. We had an equation for slope. Slope was equal to rise over run, or a little bit more algebraically, slope was equal to y2 minus y1 over x2 minus x1. So working with this and working with the 2 points that I have, do 10 take away 4 divided by 5 take away 1. A slope of 6 over 4, and if I reduce this, I get a slope of 3 halves. So I'm rising 3 units as I run 2 units. In grade 9 and 10 and even in grade 11, you would represent the equation of a line using the form y equals mx plus b, where b is the y-intercept and m is the slope. Things change when we're working with vectors because a vector has a starting point and it has an ending point. Equations of lines in the form y equals mx plus b don't have a starting point and they don't have an ending point. They go on and on forever in both directions. So how can we represent a vector, something that has a starting point, has an ending point, using y equals mx plus b? And we really can't. What we can do is define the vector equation of a line. We'll call that r, and that's going to be equal to some starting point plus a variable or a parameter, and we'll call that parameter t, times a direction. So what direction the vector is pointing in. If I take the vector that we're working with right now, we know the starting point. We know the starting point is the point 1 and 4. The harder thing to find is the direction. Well, let's look at the vector that we drew. We said slope is 3 over 2, or the rise divided by the run. Well, the rise is the y component. The run is the x component. So here, where I'm rising 3, that would be a y component of 3. If I'm running 2, that would be an x component of 2. So my direction vector would be the vector 2 and 3. Here the 2 represents the run, the 3 represents the rise, and this variable t is called the parameter. So the vector form of a line is some starting point plus a parameter t times a direction, and the direction is of the form run and rise. So using that equation, r equals 1 and 4, the starting point, plus my parameter t times the direction vector 2, 3. I can imagine a table of values for my parameter t, and then my other variable would be the vector r, and this is a vector that is starting at 1 and 4 and pointing to a certain direction. So if I choose some different values for t, I can plug these different variables for t into the equation, and now I'm essentially adding vectors together. So I have the vector 1, 4 plus the vector negative 4 and negative 6. 1 plus negative 4 is negative 3. 4 plus negative 6 is negative 2. So the corresponding vector, when my parameter is 2, would be the vector negative 3 and negative 2. Can do the same thing for the other parameters. So if t is negative 1, then I have the vector 1 and 4, take away the vector 2 and 3. Or, if you prefer, the vector 1 and 4 plus the vector negative 2, negative 3. Which gives me the vector negative 1 and positive 1. And you can try filling in the rest of this table. You should try filling in the rest of this table, and you can check your work with mine. And what we've done, if I go back a slide, by filling in this table of values for different parameters, is create a line that starts at that point 1 and 4 and goes off potentially in either direction as far as we need it to. So this is still a vector, still has a starting point and an ending point, but based on that parameter t, we're stretching that starting point or ending point, changing the direction of the vector, making it an opposite vector, and we can figure out or define any point on that line. So to formalize this, any vector can be written as its starting point plus a parameter t times a direction vector. So my vector r becomes any point on the line, and it's equal to some position vector, which we can find when t equals 0. And this really is our starting point. And to that starting point, we're going to take our parameter, which we can change to get new points on the line, and we're going to multiply that parameter by the vector that tells us which way this line is pointing. So it's a direction vector. direction vector is of the form run and rise. Or, since the run is the x coordinate and the rise is the y coordinate, x and y. So let's look at an easy problem. Let's find the vector equation of a line that passes through 2 and 1 and has a slope of 4/3. So here I'm going to use that point 2 and 1 as my starting point, or R0. So my vector is equal to my starting point, 2 and 1, plus my parameter t, times my direction vector. Since my slope is 4/3, 3 is my run, 4 is my rise, so it would be a direction vector of 3 and 4. Here's a better question. With the same equation, can I figure out if the point 6 and 8 lies on that line? And yes, we can. So I'm going to let that point 6, 8 equal the vector r. So 6, 8 is going to be equal to my starting point 2, 1 plus t times direction vector 3 and 4. And now to solve this, I'm going to break this up into x components and y components. So my x component, my x coordinates, is going to be 6 is equal to 2 plus 3 times t. So I distributed the t into the brackets. My y component is going to be 8 is equal to 1 plus 4t. So I'm going to, in both components, solve for t. So bringing the 2 to the other side of the x component, I get 4 equals 3t. For the y component, I get 7 equals 4t. Dividing both sides by the coefficient of the parameter. For the x component, I get 4/3 equals t. For the y component, I get 7/4 equals t. If 6 and 8 was on this line, my parameter would have to be equal. This is not equal. 7/4 and 4/3 are not equal, which means we can say that the point 6 and 8 is not on the line defined by the vector r. So in general, if I have some equation of a line in vector form, r equals my starting point r naught plus my parameter t times my direction vector m, I can take a coordinate that's on vector r, so some coordinate x and y. That's going to be equal to my starting point x coordinate, starting point y coordinate, plus t times my direction vector, and let's call that a and b. And I can break apart this vector equation into two separate equations where I'm looking at the x coordinates so my x starting point plus my parameter times the run. The y component would be the y starting point plus the parameter times the rise. So I've gone from my vector equation of a line and I've converted my vector equation to something called a parametric equation. And I think I'll leave you with this question to try on your own, and we will do this first thing tomorrow. Determine the vector and parametric equations of a line through the points E and F. In addition, once you've done that, find the x-intercept and find a line perpendicular to your answer. We will do this in class, but you should try this on your own first. Bring your answer to class so we can compare. Thanks for watching.